It's a pleasure to welcome Kevin Buzzard, who will talk about proving theorems with computers. Please.
Thank you very much for the invitation. I don't know if Bob is here. I was looking out for him earlier, but thank you to the organising committee for inviting me. And secondly, let me just stress that I'm not a computer scientist, right? I'm just a regular mathematician who, up until 4 years ago, was just doing regular math. Was just doing research into the Langlands program. In just the same way that all other mathematicians do research. So, I mean, 4 years ago, I kind of went down some rabbit hole. I don't really have much of a computing background either, but I went down some rabbit hole involving computers and theorem provers, and it somehow completely changed my entire academic, my viewpoint and the things I do from 9 to 5. But I'm not a computer scientist. I am a number theorist really, but I'm going to spend a lot of time talking about computers, and in particular talking about what I've learned in the last few years. Computers. I mean, a computer used to be human a long time ago. It was a human that did calculations, and there's plenty of examples of mathematicians who did calculations. For example, Riemann actually, even well before computers, Riemann could actually figure out a non-trivial zero of his zeta function, and indeed it had real part a half, an imaginary part just over 14. And Gauss, of course, he noticed the fact, he was proving theorems about, when -1 was a square mod p. This can be done, in an essentially elementary manner, or when -3 is a square mod p. These things can be done using tricks. But when you start asking questions about, when 5 is a square mod p, this is very hard, right? If you're Gauss, I mean, the natural thing to do is to just compute many, many examples of prime numbers and, try and figure out what the squares are modulo p for, all the prime numbers less than 100. This would be a very natural thing to do. And then you look at, which numbers are squares mod 5, which primes are squares mod 5, and which primes is 5 a square mod p, and you notice to your surprise that the answers are the same. And and eventually you'll discover quadratic reciprocity. But computation, is at the heart of the investigation, which leads to the brilliant idea. So then along came the computer, and then computers could do computations more efficiently. And so, for example, Birch and Dyer took an awful lot of elliptic curves and computed the number of solutions. They had an awful lot of plane cubic equations, and they computed the number of solutions to these equations modulo, all primes p less than 1,000, because they had this computer that was the size of a large room accessible to them, with a few kilobytes of memory that ran incredibly slowly and ran on valves. This is before the semiconductor revolution. But using this machine, in its downtime in the evenings, they managed to get enough data that ultimately turned into the Birch and Swinnerton and Dyer conjecture. So computers do change mathematics, and computations change mathematics, but somehow they didn't prove theory. Ultimately they turned into the computations were leading mathematicians to make conjectures, and of course Gauss proved his conjecture. He proved the law of quadratic reciprocity, but Riemann and Birch and Swinnerton and Dyer weren't so lucky, and indeed they're still open today. So conjectures are important because they drive mathematics forwards, and maybe one can make conjectures by using computers, right? By doing calculations, working out examples. But actually, I think that most conjectures are not made in this way. I think that things like the Hodge conjecture, just came from looking at theorems which are proved and trying to extrapolate, trying to find abstractions, trying to find common abstractions which explain known results. for example, theorems about integrals on things like abelian surfaces, which I imagine was where the Hodge conjecture came from. It was just humans trying to find, common patterns in theorems as opposed to common patterns in numbers. So, I'm not entirely sure that if you're interested in proving the Hodge conjecture, I'm not entirely sure whether a computer is a great help to you at all. I mean, computers have perhaps computed examples of algebraic varieties and checked various, computed various invariants. But it's not entirely clear that these things are going to help you if you want to prove the Hodge conjecture. At least, computers, as we mathematicians know them, these computer algebra systems that probably some but not all of us use. I certainly, I used software called Sage and Magma and PariGP. These are more specialized number theory systems, but certainly we teach our undergraduates how to use some of these systems. And what these systems do is, they can compute examples. I've computed examples of, Fourier coefficients of modular forms using these systems. But they are called computer algebra systems. And when you think about it, what about computer topology systems? Like that's not a thing, right? Maybe a topologist wouldn't want to use, if you're interested in certain questions in topology, you might want to use a computer algebra system, but there are other questions in topology where a computer algebra system, you can't even begin to use them somehow, because here's what a computer algebra system looks like. Let's say I want to expand out x plus 2y all squared. I just type it into the computer algebra system, and the computer expands out the answer. And what are x and y in this case? X and y are, they're not real numbers, right? Because this is true. This is true for objects in an arbitrary ring, an arbitrary commutative ring. But what are they actually? It turns out that x and y, when you dig into the system and look at what these things are, they do have a type, right? They are polynomials. They are elements of a polynomial ring. X, when the system sees x, actually thinks, oh well, this is an element of a polynomial ring over, let's say, the integers for now. But our system will be flexible enough to change it if the user starts asking about real numbers or complex numbers. But x is a polynomial variable over the integers, and y is a polynomial variable over the integers. And then we start adding them together, and it makes the system makes a new type, a system of polynomials in one variable over a polynomial ring in one variable. And the output you see here is actually a polynomial ring in the variable x with coefficients in the polynomial ring with the variable y. That's why the computer prints out a slightly counterintuitive. This is x squared plus, this is of the form x squared plus ax plus b, where a is 4 times y, and that's why it's switched around the x and the y. So the reason that this random computer algebra system can do this is because you kind of think in your head that x is a, we say things like, let G be a group, and then G is just a variable. But, let R be a ring and let X be an element of R. But really, that's not what's happening. The computer algebra system is just assuming that these things are polynomial rings, elements of polynomial variables in polynomial rings. And then if you start doing other things to them, it will start, if you take the sine of 30 degrees, the computer system will print out a real number, but you can take the sine of x in this system, and it will just print out a power series, and then x, the type of x will quietly change from a polynomial variable to a power series variable. But these things have types, and so you take a computer algebra system and then you give it a type it's never seen before. We say let x be a compact topological space, which as mathematicians, that's something we're extremely happy to say. But the computer algebra system won't be able to handle that, right? Because, these computer algebra systems, they know about polynomial rings, but they don't know about topological spaces. So if you're interested in proving theorems about compact topological spaces, and you'd like the computer to check some examples, you can somehow see that there's a problem here. And of course, even if you could say let X be a compact topological space in a computer algebra system. Why would you want to say that? You might want X to be an example of a compact topological space, perhaps a finite one. But if you don't just want to do computations, if you want to prove theorems, then a computer algebra system is not the thing you should be using anyway. You see, these systems do calculations, they do computations, they're not theorem provers. So this is the difference between the computer algebra systems that probably we're all familiar with and probably many of us have used, and these interactive theorem provers, which is what my talk's going to be about. So in a computer algebra system, you can ask the computer to print out all the primes less than 1 million, or perhaps more reasonably, print out all the primes less than 10,000, or construct a vector consisting of all the primes less than 1 million. This would be a fine thing to do, but the thing you can't do with a computer algebra system is ask the system to prove there's infinitely many primes, right? That's a different kind of question. Computing the primes and reasoning about the primes are two different kinds of things. And these systems which we show our undergraduates how to use, we just switched. We used to teach them Mathematica and Maple, but now we've actually just started teaching them Python because Python has a perfectly good mathematics library. So we show them how to do computations in Python. But in Python, you can do calculations, but you can't prove there's infinitely many primes. You can just write a program that prints out prime numbers and observe that it doesn't seem to stop. So you can use computer algebra systems to generate data. But what I've been playing with since 2017, when I got into this stuff, with a different kind of system. So an interactive theorem prover, a different kind of software. And in this software, you can actually prove theorems. You can reason about objects rather than just computing them. And the proofs, in some sense, look similar to the proofs that we write down on paper. So that's the difference between the computer algebra systems that many of you are familiar with and a computer theorem prover, such as Lee, which is what I'm going to be talking about in this seminar. So let me just show you what this thing looks like. Let me show you some Lee. How am I going to do this? There we are. Let's put that in. Let's full screen this, and let's go to. Oh, let's open the repository. Sorry, I was just talking to someone about something else. I'm supposed to be showing you this. Wonderful. Here we are. So this is the. Let me do this. There we go. So I'm hoping, can somebody just tell me that you can see something? Can you see like some kind of computer program thing?
Yes.
Great. So this is what I was doing with the first year undergraduates at my university, Imperial College London, between October and November. This is an entirely optional part of the course I was teaching. I was teaching part of the Introduction to Proof course, the sort of the standard proof, this sort of standard course. In the UK, we deal with students that have been doing a lot of mathematics at school. The school system in the UK works, you specialise at 16. So I've been dealing with students that know calculus already, or the informal version. They know the theorems. They didn't do epsilon delta arguments, but they know what calculus looks like. They've done very few proofs, but they know a fair bit of mathematics. And in this course, in their first term at my university, we teach them things like functions and equivalence relations and basic logic. The introduction to what an epsilon delta argument looks like, but we don't do any epsilon delta arguments. So this is one of the problem sheets I give out, and for years I've been giving out paper versions of these problem sheets, but more recently I've just been giving out a computer file as well. And if you want, you can do the problems in this computer proof system as well. So this is from the very early part of the course, we're just teaching about for all and there exists, basic theorems of basic logical objects. And this question says, is it true or false? Is it true that for all x there exists a y such that x plus y is 2? Right. So mathematically, this isn't challenging. You know, I would expect some students to write down the solutions on paper. But if students want, and you know, some are interested and many are not, you know, for many this looks rather daunting. But those that fancy a challenge, they can try and prove for all x there exists a y such that x plus y is 2. And we can see on the left, we don't see much intimidating stuff. And on the right, we see this sideways t, which means this is what you're supposed to be proving. And what you're supposed to be proving is for all real numbers x, there exists a real number y, such that x plus y is 2. And now the idea is that we don't do computation, you know, we don't do examples of real numbers. We're actually going to prove this theorem. So how does the proof work? Well, first we let x be arbitrary, right? Intro x. So I'm now writing in a programming language called Lean. I'm using something called tactics. So, you know, now the left-hand side of the screen will get perhaps more complicated to understand. But the right-hand side is normally quite easy to understand. Now it says x is a real number, and we have to prove that there exists a real number y, such that x plus y is 2. And x is a real number, so we have access to x. So what's the real number we're going to use? We're going to use 2 minus x, of course. There. And now you see this goal on the right has changed again. This interactive proof has now changed. We've now got to prove that x plus 2 minus x is 2. And of course, now, of course, the students run out of C, right? Because x plus 2 minus x is 2 is obviously true. But fortunately, you now use a more high-powered tactic. Let's try Lean simplifier. There we go. The simplifier is, you know, we've simplified that. We've simplified the left-hand side of x plus 2 minus x, and it's simplified to 2, which was the same as the right-hand side. So we get a little exciting thing telling us that we proved the theorem, and now we have this little error because we used to be apologizing that we hadn't proved the theorem, but now this tactic is failing because it says there's nothing to apologize for. So we can remove that, and the number of warnings in my file just went down from 15 to 14 down at the bottom here. Because we answered one of the 15 questions on this problem sheet. And now here's a very similar, if you're a first-year undergraduate, here's a very similar looking question. This says, can we prove that there exists a y such that for all x, x plus y is 2? And of course, it's the same proof, right? We just let y be 2 minus x. So we use 2 minus x because obviously the solution to x plus y is 2 is y is 2 minus x. Now this time it doesn't work, right? I mean, the quantifiers are in a different order. And it doesn't work, and we get an incomprehensible error message, unfortunately, which doesn't help at all. But the idea is perhaps if you're a student that's just beginning to work out what's going on here, then you look at this situation here where x appeared first, and then we could let y be 2 minus x. And this situation here where the system seems to not understand what x is, and that's because if you're looking at this goal here, there's no x at the top, right? Yeah, here there was an x at the top. The x was a real number, and we used 2 minus x to continue. But here, there's not an x at the top. X is somewhere later on in this term here. It's sort of embedded. We haven't got to it yet. We've got to y, right? So we can't use 2 minus x. We're going to have to use a number like 37. We could use 37. And now, because that doesn't involve an x, but now, unfortunately, we've got to prove that for all x, x plus 37 is 2, and this can't be proved. And indeed, this is a level of a puzzle game, right? And this is a level of a puzzle game as well, but this level can't be solved, so we have to actually change this. We should change this to false because question part 4b is false. We should put a little not in front of it. There. Now we've got to prove now we've got to prove that it's not true that there exists a y, such that for all x, x plus y is 2. And now you can go on and use, different tactics to try and prove this theorem. And I don't talk about the tactics in the lectures, but I give out handouts that explain, the basics of how to use these things. And the students can, if they choose, learn my course, but they can do their homework, by solving levels of a computer puzzle game. And so this is what you do, and you show it to a class of 250 people, and 200 people are not remotely interested, and 50 people are partially interested. and then, you know, people drop out, but some people get very interested, and then you realize that maybe you're onto something, but you know, you don't quite know what you're doing because you're just experimenting with this for the first time. But you find that you've created a group of 5 people that have somehow become so good at the system that after a while they're better than you are. So this happened to me in 2017. And in the summer of 2018, I just ran a bunch of projects, summer projects, just building up the maths library in Lean's, you know, Lean's maths library. And here's an example of one of the things that came out of this project in 2018. So this is, you see the copyright thing at the top here. This is copyright 2018, Chris Hughes. Chris Hughes is he's now an MSc student at my university. But when he wrote this, he was I guess a first-year undergraduate. And he proves, you know, he proves Gauss's law of quadratic reciprocity. He proves it, you know, but how does he do it? He uses Gauss's lemma and Eisenstein's lemma. This is a proof he found in a book, and he proves Euler's criterion. You know, he plowed through the, you know, there's Wilson's theorem. You see, you can understand the statement of the theorem there, but it's much harder to understand the proof, because the proofs are the kind of things which are taught in computer science departments, but not in maths departments. But you can teach them to mathematicians. You can teach mathematicians, you know, what these words mean, and then the mathematicians can speak the language, and they can go ahead and prove things like, you know, Gauss's law of quadratic, you know, the law of quadratic reciprocity. There's Eisenstein's theorem. Where is it? There's the technical lemma about something, things in a box, and there's the Legendre symbol, and there's Gauss's lemma, and somewhere in this file will be the proof of quadratic reciprocity. There's things for 2. Oh, here it is. Oh, here it is. No, that's not it. Oh, here it is. It's the one called quadratic reciprocity. There it is. The Legendre symbol P over Q times the Legendre symbol of Q over P is equal to some sign. And this is natural number division, so this is rounding down. So as I say, you know, this is incomprehensible computer code. But the thing I want to stress is it wasn't written by some professor in computer science. It was written by an undergraduate who'd taken the time to just learn the language. Because, you know, I gave them the opportunity to learn that language. So I got originally interested in Lean because I wanted to use it for undergraduate teaching. You know, I just thought it would be an interesting sort of experimental way. You know, I was concerned that at the bottom of my undergraduate cohort, I have people that think sufficiently vaguely that they can't really understand the difference between for all x there exists a y, and there exists a y such that for all x. You know, they're looking at x plus y is 2, and they're saying the answer to that is y is 2 minus x. And because they're not thinking very, very precisely and logically, they don't realize why y is 2 minus x is a solution to one of the questions, but is not a solution to the other one. So I got interested in in whether I could use these systems to try and actually hammer that point home to the weaker undergraduates. So I started using, you know, I use Lean, which is one of these theorem provers. There are many other theorem provers. I chose Lean because it was recommended by Tom Hales. But you know, feel free to choose your own theorem prover. And one advantage of Lean is it has a big maths library, and the maths library is kind of actively growing all the time. Maybe I can pull out some terrifying looking graph. Why don't I switch to, where's my graph? Oh, I've lost my graph. I will find it again. Let me go for, what am I doing? Sorry, I got distracted by the fact that I was Googling somebody earlier. I was looking for graphs, Lean Prover Community. Here you go, let me show you a graph. Contribution statistics. So here's what the maths library I've been working on for the last 4 years looks like. We've got nearly 50,000 theorems, 150 people involved, and it's, it started off with 30,000 lines of code, and just recently it broke 500,000. So, you know, I'll talk about this maths library later, but this is one of the advantages of using Lean over the other theorem provers, is that there's a community of mathematicians involved, and the mathematicians are writing, writing mathematics. So let me go back to my talk. So some of these systems are very old, and the general theory is very well understood. Computer scientists have understood how to make a computer theorem prover. But all of these systems can certainly prove that there's infinitely many primes. You know, they're all easily strong enough to do this kind of thing. But the interesting observation is that mathematicians don't use them, right? I mean, I use them now, but you know, and there's a group of people around me that use them, and most of those people in my group are undergraduates. In fact, it's been an absolute joy collaborating with undergraduates, I must say. But of course, the staff don't use them because they're sort of weird things, and doing proofs on paper is absolutely fine. So we don't use them, and so you might even begin to wonder why these things even exist if we don't use them. Because if we don't use them, who is even making them? And the answer is quite surprising. Who wrote Lean? Microsoft Research Design. A guy called Leo DeMara, who works for Microsoft. He wrote Lean. And why does Microsoft Research care about proving theorems? Well, maybe it doesn't care about proving theorems so much. Maybe they're writing a system which coincidentally can be used to prove theorems. Maybe they're writing a system because they want a super fast functional programming language that you can reason about in order to check that computer code has got no bugs. Because this is a billion-dollar industry, bug checking and bug squishing in computer science. Computers run the world, right? Code runs the world. Code is keeping airplanes in the sky right now, and code having no bugs is really important. So that's why a company like Microsoft might be interested in these things. So that's why they're interested, but I'm interested for different reasons. I got interested in whether I could use these things in my teaching, and I started in 2017 by taking the course I was teaching, the Introduction to Proof course.
Shopping there.
And seeing if I could do them in this proof system, and it turned out that some of the very early stuff, like the stuff that used e to the I theta is cos theta plus I sine theta. I couldn't do this stuff at all because e to the I theta equals cos theta plus I sine theta is in some sense a very hard theorem. Just because it looks familiar to the undergraduates.
Need help.
Just because it looks familiar to the undergraduates, unfortunately, it doesn't mean it's easy for the system, because the system doesn't know anything about power series, power series variables, and this involves a lot of stuff, and the system didn't even have the complex numbers at the time. But of course, it was very easy to make the complex numbers. I just defined a complex number to be a pair of real numbers, and then prove basic things about the complex numbers. And ultimately, sometime later, we could prove that e to the I theta was cos theta plus I sine theta. But we just had to build a bunch of undergraduate analysis from first principles. So this turned out to be extremely hard. And of course, the reason is the students think they know this stuff, but they didn't see analysis developed formally, and we had to develop analysis formally. So other things we do in this Introduction to Proof course is we do basic number theory and congruences, and there everything was much easier, because the theory of congruences, you could develop it from first principles once you know that the integers are a ring, and proving that the integers are a ring was something that was already done. Then equivalence relations came out. Equivalence relations were even easier, because then you didn't even need the construction of the integers and the proof that it was a ring. Equivalence relations just work with an arbitrary set, or an arbitrary type, as I was beginning to call them. Equivalence relations, you're just given the three axioms, and then proofs, constructions of things like equivalence classes, and proofs that partitions are the same as equivalence relations. These really follow, without too much trouble, from a very small list of axioms. So you could do these things, without using any background. You don't need the complex numbers for them, right? You don't need the integers. You don't need anything. These things were very easy to do in this system. And as I say, the course gets more abstract, and hence our perception of it is that it's getting more complicated. But to these computer-proof systems, in some sense, they're getting easier because the real numbers comes with a lot of baggage, whereas equivalence relation, comes with 3 axioms and that's it. And I was very pleased when a student that was, I was running an undergraduate club, and students would come along and we'd work on the problem sheet questions in this club. And as I say, I would get students saying things like, I didn't understand them, but then I tried doing some of the questions in Lean, and now I understand them, which I thought was a very interesting comment. As someone who's interested in teaching. So my preliminary conclusions are that actually the system is hard to learn, and it was typically only the bright people that would engage with the prospect of learning it. And if you're a weak student, then it's very difficult to learn the mathematics and learn the system at the same time. So my initial hope that that I could use it to teach weak students about swapping quantifiers, this hasn't been realized yet, and we've got to wait for the system to become easier, or the new system to come along, which became easier. But what happened was that I learned that the people that were finding the mathematics easy would, be interested in the intellectual challenge of learning how to, work one of these systems. If you know the mathematics already, then you're going to go through less pain when you're learning the system. And so something else that I've been dabbling with is rather than using it with the weaker students, my initial plan was just to use it with the very strong students and to see if I can push them much further. So for example, Chris Hughes, I mentioned him already. I pushed him to learn the proof of quadratic reciprocity and formalize that. And another undergraduate who was very good was a guy called Kenny Lau, who again I ran into when he was a first year, but clearly knew a bunch of algebra already. And so I gave him a copy of a T. McDonald and told him to go and formalize the theory of localization of rings. Because this is, again, something that even if we don't have the complex numbers, we didn't have the complex numbers at this point, or we had a very rudimentary interface for the complex numbers. But if you're going to prove theorems about commutative rings, these are much easier because a commutative ring is just like 9 or so axioms. So you type in the axioms and you're ready to go. So Lau developed the theory of localization of commutative rings over a quite, an intense but very short time period. And for me, this was evidence that these systems were kind of powerful. I hadn't really realized how powerful these systems were. But, it just demolished the theory of commutative rings. And I figured that, what's the next thing from commutative rings? The theory of schemes. So I suggested that I'm some professor. I suggested I collaborate with this first-year undergraduate to try and formalize the definition of a scheme. And along the way, you have to prove that the structure sheaf on an affine scheme satisfies the sheaf axiom, and that was a statement involving finite sets, some covered by finitely many subcovers. So we roped in Chris Hughes, the other undergraduate who I'd seen get very good. I mean, more have come along out of the closet now, or out of the woodwork. But these two were the first that seemed, obviously very strong. So between us, the three of us just worked out a definition of schemes and started proving basic facts about schemes, just sort of doing exercises in Hartshorne. So this was all kind of very cool, and but I thought that I should look at some of these other theorem provers. So I started asking around, to see how these have been done in other theorem provers, because Lean is very new. Lean was somehow only written in 2015, so it didn't really have a maths library. Some of these other systems have got very big maths libraries. But it turned out that it hadn't been done in any of the other theorem provers, which I thought was funny because this is standard MSc level mathematics as far as I'm concerned. And furthermore, I was told that because it hadn't been done in any other theorem provers, our work was probably publishable. So now I'm sitting with the prospect that this thing that had started off being some fun project is now actually going to turn into a research paper. It's now a sort of an accepted research paper. It took me several years to write it up because we were doing other things, but we rewrote the theory of schemes. Ultimately, we wrote it 3 times, and once I was kind of happy with it, I wrote it up with all the undergraduates that have been involved. So the fact that schemes are a completely standard piece of mathematics, that definitely there are people doing hard mathematics in these systems, really started making me ask questions, these systems have been around for decades, but it's not entirely clear to me how many people were asking these questions. And one question I think one could look at is one could look at the mathematics that computer scientists have been doing with these systems and step back and think, well, is this the kind of mathematics that should be being done with these systems? And is this the kind of mathematics that will attract other mathematicians into using these systems? And the answer is no. Somehow mathematics has been done in hard mathematics, but perhaps not kind of fashionable mathematics. People in my university, do research on schemes, but they don't necessarily do research on the kind of areas that are being formalized. So if these systems can handle schemes, can we make a tool that will teach graduate students about schemes in some way? Maybe we'll have to teach them the language. And then finally, if the systems can handle schemes, then how much further can they go? Can they handle even harder stuff? Because a scheme is MSc level mathematics. So let me tell you some of the theorems that have been, the results that have been formalized over the last 50 odd years. So the very early system written by de Bruijn, he and a student managed to prove basic facts about the real numbers. They constructed the real numbers as equivalence classes of cosy sequence and proved they were a complete ordered field. And if you think about it, you've seen what the systems look like. The idea is you tell it axioms, and then you can tell it basic proofs. And these things are basic proofs, really. This is kind of first year stuff. So fast forward to this century, Gontier, I guess it was maybe it was Gontier by himself. He formalized the proof of the four-color theorem. This was proved by a computer, right? The computer played an integral part in the proof. So computer scientists are kind of intrinsically interested in this proof. There's some fuss about whether it's a proof and should a proof give you insight, or this kind of question. So this proof said that if you check it for 2,000 graphs, then it's true for all graphs. So this was a very tedious proof that humans wouldn't really want to plow through. But Gontier got a computer to check that the argument was correct. I think to most mathematicians, they're very unclear about what Appel and Harkin did and what Gontier did. Appel and Harkin were using computer algebra systems, and Gontier was using a computer proof checker. Gontier went on with other people to prove a theorem that was, one of the key ingredients for Thomson getting his Fields medal. They proved the odd order theorem. Every group of odd order is solvable. So this is 400 pages of group theory. In 2017, Tom Hales formalized one of his own proofs. So Tom Hales was a mathematician. He proved the Kepler conjecture, this sphere packing conjecture. The best way to pack spheres is the way that greengrocers have known for millennium. So they had Hales and Ferguson submitted their papers to the Annals, but there was an issue because they had to check 70,000 nonlinear inequalities on the reals. They had to do 70,000 relatively straightforward computations, and they did it using a computer. It was like the original Appel-Harkin proof of the four-color theorem. So they originally had a proof that was using computer algebra systems. Well, they wrote code in C. They were using computer programs to check that things checked out, to check inequalities. They were checking inequalities in the real numbers. But the referees at the Annals couldn't honestly say that they'd verified that all these inequalities were true. And so Hales decided that he would check these things on a computer proof checker. So this is what he did. So what can we learn from this list? So we learned from the original work of de Bruijn that computers have taken the first steps by the 1960s. And we learned from the four-color theorem that nowadays, that by 2005, they're good enough to involve to check a tedious computational proof, which involves typing a bunch of large database of graphs into one of these systems. And by Feit-Thompson, we learn that actually it's not just tedious tedious proofs involving checking 2,000 cases. You know, this is an honest argument that involves proving lots of lemmas in group theory. So we learned that if you take a simple object, such as a group, that's defined by a small number of axioms, then the sky's the limit. You can prove arbitrarily complex theorems about groups. But I mean, in theory, they could check the classification theorem, but it would just involve typing a huge amount of stuff into a computer. So people are sort of reluctant to do it. So the Kepler conjecture work. We also learned that mathematicians can learn how to use the software because Hales was a mathematician. And we also learned that, again, they can formalize proofs which involve a mixture of both things, tedious case checking and also more complicated arguments. But again, about very, very simple objects. I mean, if you regard the reals as a done deal, then we're talking about free space and spheres. So, all of these things in common. This is the reason that we don't have schemes, is because computer scientists, who've been, for the most part, the people using these systems, computer scientists have been going for more intricate and complex proofs about very simple objects, rather than simple proofs about complicated objects. But we also learned that the software can resolve certain types of mathematical disputes. There was some question in the air as to whether Hales's proof was correct because it involved checking 70,000 inequalities. On a computer. Now I think this proof is accepted. I mean, the annals certainly accepted the papers, I should say. But what about more complex objects? Because the problem, this isn't doing a very good job of marketing this software to mathematicians. Because you see, I think this software has potential. I think the more mathematicians should use it. And the last part of my talk is just explaining why I think this software does have potential in terms of research. Because we've got the evidence that these proof systems can handle simple objects. But a scheme is a mildly more complicated object. It's a locally ringed topological space. So we taught the computer what a scheme was, and then we verified that these computer proof systems could handle them and prove simple things about more complicated objects. And as I say, we started doing this, developing a basic theory of schemes. But I told one of the algebraic geometers in my department that I taught a computer what a scheme was. And he instantly replied, well, I learned what a scheme was when I was an MSc student. And that's exactly right? This is, a scheme is not a complicated thing. A scheme is a lot more complicated than a group, right? So far, we've seen theorems about finite groups and we've seen theorems about spheres. And these are things that beginning undergraduates know about. So we're proving basic theorems about schemes, but somehow this still doesn't make an algebraic geometer excited. So how do I make a mathematician excited? We need something about much more complicated. So we decided to go for perfectoid spaces because it was 2018 and we all knew that Scholze was going to get, Peter Scholze was about to be getting a Fields Medal for doing, for proving some complicated theorems about complicated objects, namely perfectoid spaces, and deducing complicated, conjectures, deducing, proving new theorems about which were open problems that didn't mention perfectoid spaces and the statement of the theorem. So these were a trendy thing, especially in 2018, everyone was talking about them. And we sat down, me and a couple of other mathematicians that have become involved. So Johan Kommelin, he's great, he's a postdoc. I would recommend he should, if you're interested in how these systems have, this is a colloquium, but if you're interested, if number theorists want to hear how these systems have been dealing with, working with work of, dealing with work of Scholze recently, I would definitely recommend that you invite Johan Kommelin to give a more specialized seminar, number theory seminar or something, because he's actively involved in a very exciting project right now that I'll mention later. So what did we have to do? We just had to develop a theory of valuations on a ring and a big library for completions of rings and completions of topological groups and things like this, because we had to develop the theory of adic spaces. It involves a lot of topological ring theory. And Kommelin and I are number theorists. Masso is a topologist, and he ended up formalizing a lot of Borbacky's general topology. This is another very big book, and he just kind of plowed through teaching the theorems of the computer and found a couple of interesting little glitches in there somehow, proofs that didn't proofs that somehow said, it now follows from this lemma, and you're looking at this lemma, and somehow it doesn't follow from this lemma. And sometimes, there was something going wrong with the referencing. Sometimes it was another lemma, or or sometimes there were, sometimes there were very obscure proofs because somehow Bourbaki were proving things in the wrong order. Formalizing this, foundation topology work forced Masso to actually start reorganizing the material, and eventually, our version of Bourbaki is better than Bourbaki's version at the end of the day, and it's got no mistakes in it. So we constructed a perfectoid space. We didn't prove any theorems about it, and we didn't construct any examples either, apart from the empty perfectoid space, because you're actually building the completion of the algebraic closure of the p-adic numbers is a different problem. It's like building the real numbers. So it was really just a toy project, really. But the computer scientists loved it, and I could then start going around telling people that we taught a computer what a perfectoid space was. Do you remember we had a computer algebra system where x was a variable, but it was really a polynomial variable. We now in Lie we can let x be a perfectoid space. We can let x be a scheme. This is what you can do now, which you can't do in other systems. So these things can clearly handle arbitrarily complex mathematical objects. So now we've got all the ingredients, right? We know they can handle arbitrarily complex proofs, and we know they can handle arbitrarily complex mathematical objects. And so it's clearly the case that in theory, these things might end up being better, theorem provers than us, right? Than humans. So this is somehow one of the very long-term goals. So we should investigate this conjecture that perhaps we can teach computers to start thinking profoundly about the kind of things that mathematicians of 2021 are interested in, across the board. So this would be an interesting project, but unfortunately, we're still typing in the definitions, and after that, we've still got to type in all the theorems, or maybe we don't. I don't really know what we need, but these things aren't going to start proving their own theorems within the next 5 years, I don't think. But here's some speculation. Humans taught computers to understand a chess position in the 1970s, and then 25 years later, we had a computer program that beat the world chess champion. So computers we've already taught computers how to do the axioms of maths, and 25 years later, we're not beating the world mathematician champion, but I think that the reason this happened was because IBM got involved. And so now here we know that Microsoft are involved and mathematicians are getting involved. And maybe if we put some team together, some good things will happen. But, how did it happen in chess? I mean, IBM has apparently, this seems like an extremely large number to me. I'm slightly skeptical about this number, but this is what it says on Wikipedia. Apparently 700,000 grandmaster games were taught to this system. Which is a large number. And so how are we going to get 700 proofs of 700,000 theorems into Lie? Because right now computers, we have AI and we have machine learning, but computers really still can't read natural language. Computers can't read maths books. And so right now it's going to be the humans that are going to be typing in these things. And will 700,000 theorems be enough? I don't know. So far we've got 50,000 theorems. But a lot of them are, in some sense, MSc level, and I just really don't know. This is a problem for computer scientists. But the only thing I do know right now is that nobody knows what we can do with a large database of difficult mathematical theorems, because right now no such database exists in any of the theorem provers. And this is one of the things we're doing, is we're building a database. So the building really started. Seriously happening in 2019, because I was going around, I was giving various talks saying, how do we know maths is right, and how do we know that the classification of finite simple groups is correct? How do we know that all these hard theorems in the language philosophy are, people are claiming they can prove things, but they're not proving them, and people are going to start dying. And I was giving kind of fire and brimstone talks about whether mathematics was right and whether this stuff would save us. And then I started saying, well, we can do perfectoid spaces. So people started showing up in the chat devoted to this stuff. Serious mathematicians, sort of smart PhD students and postdocs and young mathematical staff would show up, and they would ask how could they get involved. And you teach them the language, and then you say, and by the way, we need some of this stuff. We haven't got any. We haven't got the finiteness of a class. Gauss knew in many cases that class group of a number field was finite. But the definition of the class group of a number field was in none of these systems because it's deemed too fancy. It's not the kind of thing that gets computer scientists excited. And mathematicians don't use this system. So a bunch of people proved class group of a number field was finite, and they've just written out this will become another publication. So basic undergraduate and MSc level mathematics was input into Lee's maths library in 2019 and 2020. And I kind of felt that we were in a system where we were somehow ready. If you somehow gave us a research paper that didn't rely on too technical stuff, we could maybe start formalizing the research paper. So a group of people, there was Ellenberg and Geisweit proved the capset conjecture, which was a difficult combinatorial problem. And because of all this machinery that existed already, a group of us came along and they took this Annals paper and they formalized it in our theorem proof, and we formally verified that this Annals paper was correct. So that was the state where we were at. We felt that we could kind of do things as long as they were, didn't involve a whole bunch of research level machinery, because we only had MSc level machinery. But certainly we could do undergraduate problem sheets. It's getting to this point where the system can understand the vast majority of the exams. It can understand the questions in the exam papers we're giving the undergraduates. And it can understand if you type in the solutions. But it's not really at the point where it can find the solutions itself. It has high-powered tactics that look for solutions. It try and string stuff together. And we even have people from OpenAI now working with Lee. Using their GPT system, which can be used to write news articles. They're experimenting to see if they can use that to write computer proofs. And they simplified some of the proofs in our maths library. And AI has written some of the proofs in our maths library, but the proofs are very short. But now in some sense, you can say that you give me a problem in an arbitrary undergraduate problem sheet, and I can turn that into a computer game now. I can turn that into a computer game that says your objective is to do this, and once you've done it, the computer, if your proof is correct, the computer will verify it. So this is where we were until the end of 2020, and then out of the blue, Peter Scholze himself, who was aware of the perfectoid space work and was also only too aware that we'd proved no theorems about perfectoid spaces, he gave us a challenge from some of the work he was doing post. So let me just finish with this then. In 2019, 2020, he gave some courses in Bonn about something that him and Dustin Clausen have been working on, this thing called condensed sets in liquid mathematics. And interestingly, Scholze asked me if we'd had study groups on these things at Imperial, and we had. We'd looked at these courses because they contain sort of revolutionary new material. And he asked me if we'd specifically check the details of some of the results, in one of the sections, one of these write-ups, and I told him that we hadn't checked those details. And he says that as far as he can see, he had asked several people this question, and as far as he could see, nobody was checking these technical details. And for him, the results in section 9 of this second paper were, the thing that was holding everything together. And I should mention Voivodsky. He got into one of these. He got into, Koch, another one of these systems, and worked on it for 15 years before he died prematurely in 2017. But he got into it because he was like one of the reasons I was interested. He got very paranoid. People found a mistake in one of his published papers, and he was concerned that the system we have currently, where people write things up and then they're refereed and then people have study groups on them. But once you get to the technical stuff, if it's written by somebody you trust, e.g. someone with a fields medal, then maybe you're not going to check those technical details carefully. So Scholze challenged me to check, one of the first theorems in section 9. Well, not me, he challenged my community. to check theorem 9.1, this is a statement that some X group vanishes in the category of liquid modules. This is all very serious modern stuff. So this to me looked like a hard a theorem about complicated objects that needed a complicated proof. So if you Google for the phrase liquid tensor experiment, this basically uniquely defines the blog post that Scholze wrote on my blog. So just very, very briefly, here's some things he said. With this theorem, the hope that the condensed formalism can be fruitfully applied to real functional analysis. He wants to use the techniques of algebraic geometry to do functional analysis. With this theorem, the formalism stands or falls, I think, is of utmost foundational importance. And he's concerned that it hasn't been looked through very carefully. If it stands, the theorem gives a powerful framework for real functional analysis, making it into an essentially algebraic theorem. So he talked about an example where he's co-author with some of this stuff, Dustin Clausen, proved various standard finiteness results for compact ribbon surface, but without using any functional analysis, giving new proofs without any functional analysis. And then finally, he says, I think this may be my most important theorem to date. So you can see why he wants to make sure that it's true. Better make sure it's correct. So the challenge is that can we check this theorem in our computer proof checkers? And the answer is we've started, and we're 2 months in, and we're about halfway through the hard technical work. And maybe in another 2 or 3 months' time, we'll have got to the point where Scholze is kind of happy. But we're doing we're doing some messy things. We have continuous maps between semi-norm groups, and we're kind of trying to work out what you can say about norms in statements like the snake lemma. And I think within another few months, we'll have done enough to stop him worrying. And then a few months after that, I think we'll have a formal proof of what he wants. And and what will we have gained, right? So a bunch of people will look at us and say, well, Scholze said it was true. I checked some of the details. It's unsurprising that all of the details are true. What have you actually done? What was the point of checking on a computer that it was true? And so here's maybe my answer to this question. I personally found it a very interesting way to learn Scholze's results and really learn some of the technicalities that are going into these things, because it forces you to read and understand every details of the proofs. This is in some sense the first evidence that we have that these systems can handle complicated proofs about complicated objects. So I suspected that this was the case, but now we're in the process of proving this thing. Undergraduates have been able to join in. We've needed facts about profinite sets. We didn't have a definition of profinite set when we started, but one of the key things in this thing is the pro et al topology, which is a topology on the category of profinite sets. So undergraduates have been proving stuff in point set topology, undergraduates that I've trained earlier. And it's collaborating with a big group of mathematicians. It's not like just working with 1 or 2 other experts. I'm working with anyone who wants to be involved, and people come and go. And it's quite an exciting piece of work. Scholze doesn't do the formalization, but he's always on hand to answer our questions. So it's been quite an interesting experience. And also, I should say, I don't know if I mentioned it in the slides, but 2 of the lemmas in his original write-up were not correctly proved. I mean, the proof didn't prove the lemma, and Scholze had to, reprove lemmas and reformalize things in order to get things working. And so we did actually come up with errors. They were not serious errors. I mean, you always find mistakes in maths papers, right? You find mistakes, and you fix them yourself, or you mention it to the author, and the author just sketches the way around it. You find slips, but they're not problems. So we found slips. We're not expected to find problems, but we found slips. And these slips have already been fixed, right? They've been fixed before the thing's been published. So we've done a service to the community here. So then just the last few slides are, how am I doing? Oh, I need to stop. So what's next? Maybe we could try and figure out what the Langlands conjectures say. I won't talk about this. I made a game called the natural number game. It's one of the things I used to teach people. But you can Google natural number game. We're thinking about taking on the Stacks project. It would be interesting if we can make a tool which graduate students could use to learn algebraic geometry. So there's some ideas about that there, but I won't go through that now. But ultimately, I think we're turning maths into a game. And I think that this will draw people in. At the minute, the game has a rather nasty interface because you have to learn a programming language. But fortunately, Hales and Koepka are working on a controlled natural language where you speak in some precise dialect of English, and this is translated into Lean. And ultimately, as mathematicians get more involved and start suggesting, the direction that these software should be going in, because that's been the problem for 25 years. It was going in the direction that computer scientists wanted to go in, but now it's going to start going in the direction that mathematicians are more interested in. And at some point, I firmly believe that something really scary will happen. Maybe a computer will say, I proved the Riemann hypothesis. The proof is 2 billion lines of gobbledygook. I can give you no insight as to why it's true. So I don't know when the scary thing will happen, but I'm hoping that I'll be alive when it happens. And that's the end of my talk. Thank you very much for listening. And I'm sorry I overran my 2 minutes.
Thank you.
It's always good to hear someone say thank you at the end, because you suddenly realize that you could have just stopped streaming. I could have been speaking to nobody for the last 20 minutes. It's good to know you're still there.
Great talk, thanks.
Any questions or comments?
Yes. Hello, Professor.
Hello.
I've been on the Lean Julep for a year.
Oh,
so I've done all the. So my question is how do you actually make progress after you do the real number game and the natural number game?
Oh, yeah.
How do you go from there to the stuff that your undergraduates are doing?
The way you do it always is you just choose a project. The way I did it, so I didn't even have the natural number game, right? There was no resources at all for mathematicians when I started. You could read a book called Theorem Proving in Lean, which talks a lot about type theory, and doesn't really have theory, you can learn the foundations of type theory and some basic tactics. But the way I learned was I gave myself a challenge, which was to formalize all the problem sheets on my undergraduate course that I was teaching. And then I showed up on the chat, and whenever I got stuck, I just asked a question, and I asked 1,000 questions, and then I got the hang of it. And then I did them all, and then I did schemes, and then I did perfectoid spaces. And by the end of that, I wasn't asking the questions anymore, I was answering the questions. So you need to find a challenge, and it needs to be a challenge which you understand the mathematics of. So find a piece of mathematics that you know, not that you want to learn, find a piece of mathematics that you know, and then just try and take a proof, take a definition or a proof, and then try and type it into Lean. And when you get stuck, ask on the chat. I don't know if this will scale, but right now this works very well. I'm frantically writing a book. Right? I'm writing a book called Mathematics in Lean. And eventually people will be able to read, eventually as mathematicians get more interested in this stuff, more material that's useful to mathematicians will appear, right? Right now you can plow through computer science textbooks, which will teach you about type theory, but we need mathematicians. Yeah, I need to work harder. I'll work harder. Read my book. Read Mathematics in Lean, but I didn't finish writing it yet. But
I've been working on it.
Yeah, we've started, but I just need to finish it. We need more people, right? Is the answer to your question.
I'm assuming that this body of formalization takes set theoretic axioms, right?
Type theoretic axioms, as it happens.
But you do make non-constructive set theory assumptions. So the real numbers are defined in what construction do you use, for example, of the reals?
Real numbers are equivalence classes of Cauchy sequences of rationals. And Cauchy sequences are, the field of fractions are the integers essentially. And the integers are, some monoid localization of the naturals. But then the naturals are defined using Peano's axioms. So 0 is a natural, and the number after a natural is a natural, and that's it. So that's
but you still assume something like specification, right?
No. I mean, this is kind of technical, but the logic we use is something called the calculus of inductive constructions.
Oh, okay.
So
Good.
I can make an inductive type by specifying the constructors, and then the system figures out the recursor. So I tell Lean, let's define the naturals in the following way. 0 is a natural, the number after a natural is natural. That's it. And then Lean says, okay, I'll make a new constant called the naturals. I'll make 2 constructors called 0 and the successor function. And I'll also give you a recursor. It says, if you can prove it for 0 and you can prove it for successors, then you proved it for everything. You know, so it figures out it works out what the principle of mathematical induction says from the definition, and it gives us that as an axiom as well.
I've seen some mathematicians take a purely set theoretic approach and just assume ZFC axioms in the theorem prover and then prove everything non-constructively. But
right. So then you get
your work is mostly constructive.
How do you get the natural numbers? You then say, by the axiom of infinity, do you have natural numbers?
Yeah.
Right. But then, yeah, we build everything constructively, and the rationals are built constructively, but the reals are built non-constructively. The reals are just some type of equivalence classes of kosher sequences. So we can't evaluate on them. And now the problem with that the computer scientists have is now given 2 real numbers, you can't figure out if they're equal, right? Because pi squared over 6 is a real number I can create in Lean, and sum of 1 over n squared is a real number I can create in Lean. And now we've got 2 real numbers, and we can't work out if they're equal or not, because there's no algorithm which proves this theorem of Euler. But we just say we don't care. We just assume, you know, we don't care. We just assume. The issue is we assume the law of the excluding middle. We assume that any 2 real numbers are either equal or not equal, and just press on from there. So that's where we digress from constructivists. But the fact that the foundations of type theoretic and not set theoretic is not really an issue. I mean, we've made set theory within type theory. We've proved the independence of the continuum hypothesis, and we do that by making set theory and then making models of set theory and then reasoning about those models. So we can do set theory within a language, and also meta theoretically, because the system is just powerful enough to make new systems within it.
Hi, you mentioned that there were previous proofs using computer algebra systems that had bugs in them. I was wondering, is Lean somehow more robust than older systems?
Oh, so I think all of these systems are very robust. But so the first thing that one should say immediately is that if a computer tells me that they've checked a proof, then already that's an order of magnitude. That's a much more powerful statement than a human telling you they've checked a proof, because computers are a lot more fussy. But of course, you know, computer code can contain bugs. So does Lean's kernel have a bug? And like, maybe, I've not read it, it's written in C++, right? I'm very unlikely to read it. However, here's what we can do. The way type theory works is to check that the string A is a proof of string B. That's interpreted in type theory as checking that a certain term has type equal to a certain type. And you could write type checkers that know Lean's type theory, and then just try and solve that problem independently. So when Lean says, I've checked this proof, Lean prints out a gigantic piece of gobbledygook. Well, it doesn't, it generates a gigantic piece of gobbledygook and says, by the way, this is what I think your proof looks like. And now the question is this proof valid? Does this proof actually follow from the axioms of type theory? And now you can get independent programs that look at that gigantic proof that Lean has produced and verify. You know, these programs are very short and they're written in several programming languages, and you can take them, all of them, and independently run them all on this gigantic proof term and verify that it is indeed a proof of the theorem it's supposed to be proved on. So if you're uber paranoid, that's the kind of thing you can do. So by this stage, you could run proofs on different operating systems, on different computers, using different chipsets, and you completely avoid having to rely on Lean's kernel.
But But is it straightforward to transfer theorems from one system into another?
No, it's impossible. It's impossible. So I'm putting all my eggs in this lean basket, and I go around telling mathematicians that, you know, I mentioned several other theorem provers. You can use whichever theorem prover you like. However, I will mark that lean has this gigantic, vastly growing mathematics library and a whole bunch of mathematicians working on it. Whereas these other systems, although they're pretty spectacular in their own ways, but they don't have the community that we've built with lean. So, it will be harder to work your way in, but it will certainly be possible. To be quite frank, I don't think that lean should be the one theorem that ends up being the one mathematicians use. I think that we should have competing things. I mean, a monopoly is no good. Go away and learn another theorem prover, and then just see if you can encourage growth in that theorem prover in the direction of MSc level mathematics, because that's where it's not going somehow.
But in principle, would it be possible to make like a Google translator between different systems, or is it super hard?
So surprisingly, so people ask this about programming languages, right? I've written a program in C. Can I translate this into a program in Python? Or I've written a program in Python. Can I translate it into a program in C? And the answer is, I mean, it can be done, and there are systems which do it. However, people argue that you don't really want to do it because the resulting thing you get is kind of incomprehensible and is not written in the idiomatic language of the prover. Somehow, for example, if you've got a proof that uses set theory and you translate it into a proof that uses type theory, then there'll be a whole lot of fiddling around because of the slight differences between set theory and type theory. That will, and you'll have certain theorems you want to argue in a set theoretic way, and certain theorems you want to argue in a type theoretic way. And so things will get mangled as you move between the theorems. But yeah, I don't see why it couldn't be done. Why would you want to do it? Well, all the systems are the same. So
Also, that not to repeat the job.
Yeah. But if you translate something that's human readable, you might get something that's not human readable. Yeah, I think you're right. Actually, just thinking about it more, the reason that people have told me that this is unwise, computer scientists have laughed at me for asking this question, because they say you get good C code and you translate it into Python, you get crummy Python code, right? Or you get good Python code and you auto translate it into C and you get crummy C code. But actually thinking about it, you don't really care if it's crummy or not. If you can read the maths proof and then you've got the computer saying, yeah, this is a proof. And someone else wants to use that proof in that system to do something else.
But
yeah, who cares? A proof is a proof, right? Who cares if humans can't read it? I don't know. So yeah, maybe you're right. Maybe more attention should go into this kind of question.
On the note of transferability, Schulman mentioned to me that there was a formalization of spectral sequences in homotopy type theory, and that was done in Lean, and that was done in one of the earlier, yes, and then Lean's dropped support. And now it is in a limbo state where it only exists on an old version.
That's right, yes. But we'll get to it in the end. But you see, this is a subtle thing, right? This spectral sequence was proof for spaces, right? In this synthetic sense, space is kind of axiom. A space isn't a topological space up to homotopy, or a topological space up to whatever they call those funny those suspended homotopies. A space is just a type for them. And if we were to formalize it in Lean, we would formalize it for actual topological spaces.
Right.
So somehow it's a little bit different.
It's a different foundational system.
Yeah, but the statement of the theorem is different as well. You ask people in some of these systems, and they say, oh yeah, we've computed pi4 of S3. But when you actually look at what they've done, they haven't computed pi4 of the topological space S3. They computed pi4 of some kind of combinatorial gadget, which has been defined using some kind of inductive construction.
But then there exists cohesive type theories, and you can find a link to the actual spaces.
Yeah, exactly. But what I'm saying is, if you want to introduce another type theory, now you've got to translate. I mean, it would just be right now. It would just be easier to reprove the result in Lean 3 or Lean 4. Right? We have Lean 4 now. Yeah. Already, we've got the question of how to translate the maths over from Lean into Lean. You know, and already that's a phenomenally difficult problem. And Lean 3 and Lean 4 share the same type theory, but we've got 500,000 lines of mathematical proofs that we want to use this new version of Lean on. And you know, computer scientists are working very hard on, you know, making that happen automatically. But ultimately, I think at some point we're going to have to, you know, do bits of it by hand.
So can you do estimates? If I'm just a naive question, so what kind of inequalities are embedded into this Lean program? Can you check? Can you check like verify some inequality, some sequence?
Yeah. We can do Cauchy-Schwarz, things like this, basic stuff. I'm involved in a team together with some people in Microsoft, which are interested in getting Lean to solve IMO problems. And inequalities do show up there. So we've been playing with doing IMO level inequalities. So yeah, that gives you some kind of indication as to the kind of things we can do. But inequalities are unfortunately, it's difficult. They are actually some kind of, there's some theorem that says that, I think that there might even be an algorithm to solve all inequalities in some sense, or at least on the reals. But the algorithm will never terminate in practice. And also inequalities are going rather out of fashion for the IMO, it seems. They tend to show up less and less. So,
with the IMO Grand Challenge, the goal is to have an AI solve them, right?
Right, yeah. But somehow it would be nice. Yeah, but we just kind of goof around solving them ourselves and try to work out what we're actually doing, right? Try to find common patterns.
Oh, could I ask another sort of dumb question? Sorry, it's getting kind of late, but about the library business. So is it possible to have a bug in the library in the sense that, you know, some undergraduate puts in some piece of math that's actually wrong, and then that it somehow leads to wrong, or is this logically impossible?
I don't think that can happen. I mean, what you can do is you could prove a theorem that isn't the theorem you thought you were proving. You could prove a theorem that isn't the theorem you thought you were proving. Right? You could fail to correctly state a theorem, and then you could prove it. And then you could prove the incorrectly stated theorem. And then when someone tries to apply it, they realize that, you know, there's some problem. But if the system says the proof is correct, then the proof is correct. And as I say, in the background, we have all sorts of other systems which are checking the output.
So it is not possible to somehow give the system wrong information or something like that. That will lead it to sort of make wrong.
You can't get it to assuming mathematics is consistent. You can't get it to prove something false. You can you can cheat, right? Some theories, if you don't fill in the proof, you can just put sorry, and then the system will temporarily accept it, but it will mark with, you know, if you compile the code, you'll get a warning saying that at some point somebody cheated. And when we were making perfectoral spaces, this is absolutely what we did. Yeah, we had to work from the bottom up, developing a theory of topological commutative algebra, but we also wanted to work from the top down. So very early on, mathematicians could see us type, you know, there'd X be a perfectoral space. So it would compile, but with warnings, and then eventually we glued everything together, and then it compiled without warnings. But yeah, just because I've said we define perfectoral spaces, you still actually have to go and look and check that the definition I put is the definition that's in the books, right? Because I could just be lying. So there's something I could call something perfectoral space, but just, you know, define it to be the natural numbers. And I could say let X be a perfectoral space, and X would just be a natural number. So that's the kind of thing you can do, but, you know, it's not so clear that it's helpful.
So another question. So can the computer catch some mistake that, for example, we do a proof where we prove that something is a constant, but that turns out that it depends on some other things that we didn't think of? Can Lean then say, oh, at this line you did a mistake here? Or is it that everything is not working and you have to just decipher?
Well, what happens is you have to type these things in, but you type proofs in manually. So you type in the proof, and when you get to the bad point, the computer says, okay, I can do everything except I can't figure out how to prove this bit. And you either look at it and think, oh, I can prove that bit, and then you tell it how to prove it, and the AI gets a bit better. Or you realize that you can't prove it, or you don't know why the computer's asking, and then you have to start trying to figure out what the computer did. You have to know the maths proof yourself, right? The computer is just letting you step through the maths proof. Except every now and then it does 10 steps itself, right? Because, every now and then it says, it sort of says, oh, okay. You say, now we want to get to this point, and the computer's like, oh, I can get there myself. And then you say, now we want to get to this point, and the computer's like, well, perhaps you can guide me there. So if there's a bogus proof in the literature, then when you're typing it in, you realize that you can't get the computer to understand it, and then you have to start thinking about what the proof actually is. And then you start trying to understand the proof as a human. And if you can't understand it as a human, then you have to go back to the author of the original thing. So that's
thank you.
There was an interesting story about one of our gang, Sebastian Goertzel, typing in a proof in another system in Isabelle of a result of Vladimir Schur into Isabelle, and he got stuck, and he didn't just get stuck. There was an inequality that was an inequality that accidentally been transposed in an argument, and the entire proof broke down. And Goertzel and Schur worked together to fix the proof, and their fixed proof, they just typed it all into Isabelle, and they just typed the whole thing in. Any more?
Is it realistic that computers can prove soon like simple lemmas, and then mathematicians can split the proof into sequence of simple lemmas and let computer do the rest?
Well, I
So you
mean,
did, yeah.
we're somehow trying to do it. Depends. It very much depends on what kind of mathematics you're doing. So one thing we've had a lot of success with recently is category theory, which I find it rather dry and arid. But actually, category theory is quite complex in the sense that you're forever doing things like, well, this is an epimorphism, and this arrow is an epimorphism, and this arrow is clearly isomorphic to this arrow because I've got an isomorphism of the source and target objects, and the diagram commutes. So therefore, this is obviously an epimorphism. But somehow the computer has to be told, sometimes has to be told a lot of hints. When you're trying to prove these things by hand, it would be hard work. And so people have developed tactics which can try and do chunks of category theory, and yeah, it's sort of going fairly well. For example, you state the Uneda lemma, and then you ask the computer to prove it, and the computer just finds a proof. But somehow the power of the Uneda lemma is in the statement, right? The ingenious idea is in the statement. You show the Uneda lemma to a PhD student, they can find a proof. But you show it to Lean, it can find a proof as well. So that's the kind of thing it can do. But yeah, breaking big things up into complicated things is more difficult. Yeah, we're years away from the revolution, but we're certainly not years away from being able to use it to, talk about interesting mathematics. More and more people should be able to state the theory, state the conjecture they're currently working on. Within the next few years, there should be, we're really hoping to get a really kind of comprehensive collection of definitions in there. So if you're working on schemes, if you're working on schemes or perfectoid spaces, you might be able to at least state the theorem you're working on. That's somehow the first goal.
So does Lean suggest you to apply some techniques? For example, I don't know, you could apply Cauchy-Lipschitz theorem here because
you can ask. Yeah, you can absolutely ask it to do things. Currently, it's kind of lousy at doing it. In fact, currently it often looks at the goal and says, "Oh, your goal is A less than or equal to B." So you could maybe find C and prove that A is less than C and C is less than or equal to B. Or you could maybe find C such that A is less than or equal to C and C is less than B. Or you maybe could, it sort of produces kind of 100 kind of trivial things, which somehow aren't much used. That's the current status of the suggest algorithm. But as people will eventually this is the collaboration. This sort of thing is sort of halfway between mathematics and computer science. It's trying to get computer scientists to train computers to think like mathematicians. But these are hard questions, and it's really a young area in some sense, because they've got very good at pushing these theorems. They've got very good at pushing these systems towards computer science, but we really want to push them towards research mathematics now. And so it's a new collection of questions is appearing. And so it's all very much a work in progress.
Thank you.
Okay, if there are no more questions, then thank you again.
Thank you very much for coming. And thank you for the